For multielectron wave functions, we've talked about the fact that you can write them as a product of one electron wave functions, as I've done up here, but that's not necessarily going to lead us to the most accurate answer. However, it is appealing for a couple of different reasons. Okay, one of these is that it's easy to manipulate, that is to say manipulate mathematically. It's easy to manipulate this kind of wave function and solve for this particular solution for the Schrodinger equation. Another thing that's good about it is that it's easy to interpret. For whatever reason, it's easier for us to think of electrons as inhabiting one electron wave functions and just adding them together by making the product of all of their wave functions. Okay, so that interpretation is what sort of leads to the orbital model that we all learn in general chemistry. And so this is really at the basis of that orbital model. But what I want to consider here is how we might go about actually finding the best possible result for a system if we are using this assumption. So I want to make it clear that this is an assumption that we can write this wave function exactly this way. But there are times when that's not going to be the best way to write the wave function. And at that point, we'll have to do something a little bit harder. Okay, so let's start off by talking about helium, and I'll remind you that the helium Hamiltonian can be written as follows. We can write Laplacian for electron 1 minus 2 over R1 plus a term that would be the Laplacian in electron 2 minus 2 over R2. And you can see in atomic units, man, it's sure a lot easier to write these Hamiltonians down, isn't it? So just to remind you, this is the kinetic energy of electron 1. This is its Coulomb attraction to the nucleus. And this is the kinetic energy of electron 2 and its Coulomb attraction to the nucleus. The nucleus has 2 protons, and that's why we have a 2 in here, the numerator. Now these 2 electrons, if this were all there was to this Hamiltonian, this would be an easy problem to solve, because this would be just like 2 hydrogen atoms with a little bit more charge on the nucleus. But instead we have this additional term, R12, and that's what sort of fouls things up for helium. All right, so what we're going to do is we're going to approach solving this Hamiltonian, the Schrodinger equation that is based on this Hamiltonian, but we're going to do it for a wave function that is a product of the two parts. Now I'm going to take another step further here for helium, and that is for the lowest energy state, we're going to make the assumption that both of the electrons inhabit the same spatial function. So in other words, when I write this out, I can write it as phi1 of R1 times phi1, same function, of R2. Okay, and that's not always going to be true, and it's an easy thing to change if we need to, but I just want to make that clear. By doing this, it turns out there's only one function we have to solve for, and that's this phi1. All right, so now what are we going to do to solve this equation? Well, here are the steps we're going to take. All right, I'm going to take our initial phi1, and I'm going to call that phi1 with a 1 superscript, just to label it, because this is our initial attempt. And this is going to be something that we guess. Okay, it could be a hydrogen atom orbital, but it's something that we think is going to be a good solution for the problem. All right, now we take this guess, so I'm going to call this step 0 because it's really before we get started. We're going to take this guess and we're going to use it to calculate what would the other electron feel if one of the electrons was in this orbital or this state. All right, so what we'll do is define the effective potential. So I'm going to write V effective. This is the effective potential, say, for electron 1. And we're going to get it by, essentially, it's going to be both its Coulomb term, which we'll include, but the effective potential is going to be a term that is the average over our guessed wave function for electron 2. So we're going to assume that electron 2 is in this function that we've guessed. So I'm going to put the little superscript up here, and this is going to still be that function, but now it's referring to electron 2. That's why I have the R2 here. Okay, so I want you to be sure you understand the notation. This is the function that we're optimizing, but this is the guessed version first. It is used to tell us where electron 2 is. We're going to then put this term that we have to figure out in here, and then we'll also bracket this with another version of this with R2, and we're integrating over R2. So notice we're only integrating over R2, and that's why this ends up being a function of R1. This term here implicitly has both R1 and R2 in it. In fact, we can think of 1 over R12 as basically being equal to 1 over the absolute value of the difference between these two positions. All right, it's the distance between those two electrons. So in effect, we're using an integral to help us calculate a function for R1. All right, now how can we use that? Well, in the second step of this, we're now going to solve an effective Schrodinger equation. And that effective Schrodinger equation is going to use a Hamiltonian that is based on this effective potential. All right, so what does that look like? So what we'll be calculating is the action of our effective Hamiltonian on our wave function, and we're specifically referring to a wave function of the first electron because we've got an effective potential for that first electron. And this is going to be equal to this string of operators. Okay, remember this was just the initial part, this piece of a Hamiltonian, but now we have this effective potential, and that effective potential is essentially in coordinate R1. And this is going to be operating on our wave function too. And so this is the equation we're going to solve, and we're going to solve it by, some means. It could be a variational calculation or a perturbation theory, but we're going to solve this somehow. And when we do, we'll get an effective energy out times this wave function. All right, so the solution for this equation is going to give us a eigenvalue, and it will also give us a new eigenfunction. Now I want to be clear that this function that we get out of this equation is not necessarily the same as the one that we put in at the beginning. We used this one to define our effective potential. But now that we've solved this Hamiltonian, we solved the Schrodinger equation, the solutions to the Schrodinger equation are likely different functions. They may not be a lot different, but they're different functions. All right, so this is an eigenfunction of this effective Hamiltonian. And this E effective is an eigenvalue of this effective Hamiltonian. So that's what we're doing here. All right, so this solution, I'll make it more explicit, this solution that we have come up with is basically providing us with an energy level and a wave function that are now updating the wave function. All right, since it's an updated function, what I'm going to do is I'm going to put a little superscript on it. Now this is the second one. The first one was the one we guessed at the beginning. Now this is the second one. Well, now that we have this updated function, guess what? We can repeat the sequence of steps. So we're going to come right back up here. We're going to calculate a new effective potential. We're going to use that effective potential to solve a new effective Hamiltonian. We're going to get a new set of E effective and phi for that electron, and eventually we'll go through this enough, we'll get a result that doesn't change anymore. And this is a technique known as a self-consistent field solution. And I'll put in parentheses SCF because that's how it's always abbreviated. All right, and it turns out that this self-consistent field result actually is relatively easy to implement on a computer. It's not something you'd maybe want to sit down on a piece of paper and figure all this out. But it is something that can be easily done on a computer, and there are many routines that one can use for this. All right. Now I'll point out that if we somehow used a function or a functional form that was extremely flexible and was as flexible as we could get, this stipulation that we've made for this 2-electron wave function actually means that the best we can do, so the best solution, is an energy of e to the minus 2.8617. I'll remind you that minus 2.9033 is the exact result. So even though we've used the best possible wave function here, this is as far as we can get. This is as close as we can get to the right answer. And this is something called the Hartree Fock limit. Let me write that down here. The Hartree Fock limit. And it's the best we can do, and it is limited by the fact that we have used a product of two 1-electron wave functions. That's the pure thing. We've got the very best 1-electron wave functions that we could possibly get from this, but this is as good as we can do. It's as far as we can go for this particular system. Now, I'll note that the thing that's missing here inherently is that we're not allowing the two electrons to correlate with one another. So you can imagine if I've got an atom up here and a nucleus down here, and I've got a couple of electrons in here, the way we have treated this is though this electron just feels some sort of averaged set of interactions with this electron, wherever it may be in this cloud. Okay, and that's not really what's happening. In fact, when this electron is closer here, it's a stronger interaction. When it's far away, when it's over here, it's a weaker interaction. So there's going to be some sort of correlation between the motions of those electrons. And we can't take into account that correlation when we use a wave function of this type. So in effect, what we end up doing is we define what we call a correlation energy. And that correlation energy is simply the difference between the exact energy and the energy of the Hartree Fock limit, which I'll call E sub HF. And it's this correlation energy that we often try to devise even more fancy ways of calculating results for these things so that we can get closer and closer to that exact result. But it will require us to move beyond a product of 1-electron wave functions.